Alright, 3.4. This should not be as long as 3.3. That was a very, very big section. So 3.4 is the derivative as a rate of change. A couple word problems essentially is what we're going to go through, but we want to kind of discuss where this stuff comes from. So what we know, and this is not new to us for the very first part of this for 3.4. So the derivative as a rate of change. The first definition is they talk about instantaneous rate of change, and we've already defined that instantaneous rate of change at a particular point. Rate of change. At the point x equals x naught is, and then we already know this, it's f prime of x naught. So f prime of x naught is going to be equal to the limit as h approaches 0 of f of got messy, f of x naught plus h minus f of x naught all over h. So it's something that we've already been with, provided it exists. Now, one of our very first examples come down to, and man, I've basically stolen this from the book. I'm not as impressed with, but maybe I need to discuss it because it's better in words than it's better me discuss it than you read it. So, what we want to do is we want to determine how a circle's area changes with respect to the diameter changes. So, how does the area of a circle change when or with respect to the diameter changing? Okay, so what we know is that a circle is just kind of a little picture here. We know if we have a circle here, our diameter is this piece right here. So this is our diameter d. What we know is as d changes, this area changes, but that change is not, it's not linear. It's not one-to-one because your area and diameter are actually related through. They're related through a quadratic equation. So as the linear change, as the diameter changes linearly, the area is going to change quadratically. So the areas are really connected through that particular formula. So our solution here, and I want to show you where it comes from. What we know is that our area is equal to pi r squared. So I don't want r in here. What I want is I want d in here. So we know that if d is this, then r is this, right? R is going to be from the midpoint over, so that would be r. So what we know is that r and d are related. That r is equal to 1/2 d. So what I'm going to do is I'm going to plug that in here. So that means the area is equal to pi times d over 2 squared. So what they give us in the book, they give us the formula that this is going to be equal to pi over 4d. That's squared. The reason why it's 2 squared is 4 and d squared is d squared. So that's what they're getting. So pi over 4 times d squared. So what my question is going to be is how fast is, or how fast does the area change with respect to the diameter when the diameter is 10 meters. So what we know is that they're asking for dA dt, the derivative of, they want to know how fast this is changing with respect to this. So what they're asking for is they want to know what's the derivative with respect to A, so the derivative of A with respect to t, when t is equal to 10. That's what they're asking for. Well, if this is A, what I know is this is the same thing essentially is A prime, because A is a function of t. So they want to know what's A prime when t is 10. My bad, not t, but d. When d is 10. When d is 10. So let's take the derivative. Well, the derivative of A with respect to t, dA dt is going to be the derivative of this. So this is going to be the derivative with respect to t of our d. I don't know why I keep writing t in there. Of d, dAd, dAdd, dAdd of pi over 4 d squared. So we're taking the derivative of this thing where d is our variable. So what we know is that that this pi over 4 is a constant. So I'm going to pull that pi over 4 out, and then I'm going to take the derivative of d squared. We'll just think of it just like x squared. The derivative of x squared is 2x, and the derivative of d squared is 2d. So the 2 goes into 4 twice, so this is going to be equal to pi over 2 times d. Times d. So that's the derivative of that thing. Now when d is equal to 10, so dA dd evaluated at d equals 10 is going to be equal to pi over 2 times 10. So this is going to be equal to 5 pi. All right, it's hard to see this picture. It's essentially hard to see that picture, but really what we can kind of do here and stuff it over here is, if we look at the axis, this would be the d-axis and this would be the a-axis. That a is related to d but quadratically. So if you looked at that curve, it looks like this. So as d increases, a increases quadratically. As d gets bigger, a increases by d squared. Well, 1/4 d, pi over 4 d squared. So what they're asking for is that at 10 right here, they want to know the slope of this particular tangent line. Well, the slope of that tangent line says, well, find the derivative of this green function, this green function, find the derivative of the green function, and then plug in 10. So that's what we did. Find the derivative of the green function, and then we plugged in 10. So with a lot of these, what we have to do is when they ask you, can you determine how one changes with respect to the other? Well, what you need is you need an equation that relates the two. So area and diameter are related through this. Once you know that related equation, if they want to know the rate of change, well, the rate of change is quite literally the derivative, so the instantaneous rate of change. So take the derivative of both sides and plug in whatever value they're asking for. So see if I can come up with a quick one. Let's do some motion, because that's what most of this is about. Motion along the line. So this could be horizontal motion, or this could just be strictly vertical motion. A lot of times we just talk about vertical motion for a lot of our examples, because we like throwing like balls straight up in the air. Now the only reason why I do this motion on a line is because we're only going to be one-dimensional here. You know, we only have one variable. Therefore, and well, we have we have distance as a function of t, so we are doing this over time. So really, when it looks like it's two-dimensional, which it is, but one of the dimensions is time. So that's why we're only along a line. We're just talking about how far we're moving along this line with respect to t. Now, if you do graph this like a graph where the horizontal axis is t and the vertical axis is that particular distance, then it'll have that two-dimensional curve to it. But in real life, when we're throwing something up and down, like a ball might go up and then come on back down, really that's two-dimensional. The ball is here at a particular time, here at a particular time, here at a particular time, and then all the way back down to the ground at a particular time. So the motion as it sees with our eyes is just straight up and down. But if we graph that motion over time, like make that horizontal axis time, you'd see that nice looking parabola. So time is kind of like a hidden dimension to us. We don't usually, you can't see it graphed in life unless we're throwing it horizontally as well. Okay, so this is going to be position, displacement, velocity. This is some of my favorite stuff. I like physics are very interesting. Speed. It's nice to know how the world works. Acceleration. And jerk. So let the coordinate line be called the S-axis. The reason why they call it S is because sometimes our line is horizontal, sometimes our line is vertical. So if we call it X or Y, we already have some biases that X is horizontal and Y is vertical. But if you call it the S-axis, then it can be in any orientation we choose. Now, so the position So the position S at time t is given by the function S is going to be some f of t. So its position is a function of time. So this is called our position function. Again, they call it S because the orientation of the axis can be whatever we need for the particular situation. Displacement. Displacement is just quite literally how far S moved. So this is just a change in position. So if I take a particle and move it here, its displacement is that distance. So your change in S is equal to f of t plus change in t minus f of t. It's going to look a lot like what you guys are used to. Remember, like your f of x plus h minus f of x. Now your h is just some particular move, but since our inputs are time, they want to make sure that this is the original time plus however much time elapsed minus the function at our original time. Average velocity. Average velocity, they say v average is equal to our displacement divided by our travel time. This quite literally is the slope of the secant line. So f of t plus change in t minus f of t all over that change in t. Again, this kind of takes the h position essentially. Velocity. Velocity is actually our instantaneous velocity. So this is the slope of our tangent line. So that means I'm going to take the limit of this thing as change at t goes to 0. So v of t is the derivative of s with respect to t is ds dt, which is going to be the limit as change in t goes to 0 of f of t plus change in t minus f of t all over the change in t. So it's just a limit of the secant, of the slope of the secant line. our speed is the magnitude. It's the absolute velocity. This is going to be equal to the absolute velocity of v at t. So this is the absolute value of the derivative of s with respect to t. So when you look at your accelerator, when you look at your speedometer, your speed is an instantaneous rate of speed, and it's essentially this. They're just taking the absolute value of whatever the magnitude of velocity is. It doesn't care if you're going forward or backwards. If you're driving backwards, it still says you're going 10 miles per hour. Instead of saying negative 10, it still says 10, so that's why they're taking the absolute value. So what it does is it gets direction out of there, just whatever the magnitude is. Acceleration. Acceleration is it's the derivative of velocity with respect to speed. So this is it's the change in velocity is really what this is. This is your change in velocity with respect to t. So that means a of t is going to be equal to the derivative of v at t, which happens to be the second derivative of position. And then when we talk about jerk, jerk is just it's the derivative of acceleration. So to kind of say that you can keep going further and further and further. So I guess the idea is when you feel that particular jerk, that change in acceleration, but it doesn't really, so far I have not, I've never used jerk for anything in physics. So your change in acceleration, really this is j of t, I guess, for the lack of a better letter, is going to be, this is dA dt. It's just a derivative of acceleration. But we're going to stop at acceleration for everything. So, to recap, the things that I really, like, the big stars of the show is, we know that S is the same thing as f of t. So, really you can say S of t is f of t. We know that, so this is our position. Our velocity, v, is going to be equal to the derivative of s with respect to t. This is our velocity. The magnitude of this thing is your speed. A of t is going to be equal to the derivative of v of t, which happens to be equal to the second derivative of s of t. This is acceleration. So what's kind of neat is position, velocity, and acceleration are all just derivatives of each other. So if you know this, then you know this because you can take its derivative. If you know this, you know this, you can take its derivative. So if you know any one of these, actually what's nice is we will learn how to go back and forth later in calculus. Right now we're just going in this direction. I can give you a function, you can find all its derivatives. Eventually you'll be able to find all its antiderivatives as well. So if you have any one of these three, you have all of them, which is awesome. That's why they can use acceleration to determine your velocity. So they're like, hey, I see your skid marks. You must have been this fast. Well, it's because these two functions are related to each other through derivatives. I want to do my own example. I'll do it in a second. Okay. So let's start out with an example that's going to look just like the book, like 1 through 5. So example given s is equal to 3t squared minus 3t plus 1. Where 0 is less than or equal to t, which is less than or equal to 3, and this is going to be n meters. I want to find the body's displacement. And average velocity over the interval. So the interval given is this 0 to 3, okay? This is our interval. So what we're saying is this particular particle is moving like this function only from here to here. So what's interesting about this is I'm not exactly sure what it looks like, but what we know is graphically it kind of looks like this. We have some s-axis, so this is s. We have a particle that's going to start somewhere. Who knows? I don't really know what it looks like exactly, but what we know is that over time this particle is going to move in particular positions. So it's going to move. Sometimes it'll move backwards. Sometimes it'll keep going back and forth. So really we could have a particle that moves like this over time. So like 1001, 1002, 1003, 1004, and so on. So it could look like that. So what we know is we know particular positions at any particular time. So wherever it is on the s-axis, like 0, 1, 2, 3, -1, -2, and so on. So maybe at time 0 it's equal to 1, at time 2 it's 1.5. So remember, this is a function of time, where time is going to be in seconds and s is going to be in meters. So that's what we're looking at. So in order to answer this question, what we know is displacement is just it's our displacement. And it's going to seem silly for me to write this out, but it's pretty straightforward. It is f of t plus change in t minus f of t, right? So t is going to start at 0, and the change in 3 is going to be equal to 3. So where t starts at 0 and the change in t is going to be equal to the distance of that interval, so 3 minus 0, so the change in t is going to be equal to 3. So what's neat about this is going to be f of 0 plus 3 minus f of 0. So this is equal to f of 3 minus f of 0. So your change in position is just how far did it go at time 3 subtracted from the original position. So this just simplifies to kind of exactly what you expect. That's why they give it this particular notation. So it's the function at the final time minus the function at the original time. So just figure out how far it moved. How far did it go when it was from when it moved 3 seconds? So f of 3 is going to be 3 times 3 squared minus 3 times 3 plus 1, minus, when I plug in f of 0, is going to be 3 times 0 squared minus 3 times 0 plus 1. So 27 minus 9 plus 1 minus 1. So I get 18 meters. It's moved 18 meters. Next, I want to know its average velocity. Well, what we know is the average velocity is the difference quotient. So it is equal to f of t plus change in t minus f of t all over the change in t. Over that particular interval again, okay? Now we know all these values. F of t plus change in t for this thing was just f of 3. We just did this, right? F of t is going to be f of 0. Again, remember, we just figured out that numerator. It's right here. It's final minus initial. All over the change in t, which we know is 3. So the displacement gives us the numerator of the average velocity, which is 18, and the change, and then all over the change in t, which was 3. So this is 6 meters per second. I don't know what they said time is, whatever, times in seconds now. And I didn't define it. So we'll say it's in meters and times in seconds. So the average velocity was 6 meters per second. So 6 meters per second. Because remember, it was 18 meters over 3 seconds, right? If it moved 18 over 3 seconds, because the bottom is time, and the top is distance. If you make this 6 over 1, which is what you're really simplifying, this is 6 meters per 1 second per second. So when you simplify a fraction, you're doing per unit, because the denominator becomes 1. All right, B, I want to know what's its speed and acceleration at the endpoints. The speed and acceleration at the endpoints. So what I mean by that is t equals 0 and t equals 3. Okay, that's what we're looking for. So in order to find the speed, you know the speed is the absolute value of the velocity. And actually, in order to find the acceleration, you also have to find the velocity because the acceleration is the derivative velocity. So we're going to start out with the velocity. Well, the velocity with respect to t is the derivative of s. This is essentially it's s prime of t. I should just write it that way. It'd be so much easier. Instead of saying ds dt, velocity is just the derivative of s. So since s is equal to this function, that's going to be 6t minus 3 plus 0. Derivative of 1 is 0. So this is the velocity. So at the endpoints, v of 0 is going to be equal to 6 times 0 minus 3, and v of 3 is going to be equal to 6 times 3 minus 3. So I get a velocity of negative 3 here, and 18 minus 3, I get a velocity of 15 here. It is what it is. So it looks like this really what it's saying is this thing is not starting from rest. At time 0, it's already going negative 3 in the backwards position. So remember we had our axis, so our s-axis. So at time, at t equals 0, it's already moving 3 units in this way, well, a speed of 3 units per second this way, instantaneous rate of speed. So the speedometer at time 0, is negative 3. If you want to know its exact position at time 0, if you look at it, if you plug in 0, you know that this is going to be 1, right? So you plug in 0, you're going to be 1. So at time 0, you're equal to 1. We've already figured that out, right? It was equal to 1. At time 3, it was equal to whatever that is, 19. So at time 0, it's equal to 1. It's already going this at negative 3 units per second. So it's going that way, negative 3 units per second. Remember, this is a quadratic, you know what? It can turn, so that's why it's going negative here and positive here. Okay, so 16. All right, so that means its speed would be equal to positive 3 here, and the speed here is going to be equal to 15 here, okay? It's just the absolute value of those numbers. Acceleration. A of t is equal to the derivative of v of t, because it is dv dt, right? So a of t is just v prime. So since, remember, this is going to be the derivative with respect to t of v, which was 6t minus 3. So I just have to take the derivative of v. So this is just going to be 6. So the acceleration is equal to 6 always. So the acceleration is equal to 6 always. So at the endpoints, it's 6, because you notice how there's no t value? It's always going to be 6. Now, that's not really unusual for the world. In our world, our acceleration is not 6. Our acceleration is the pull due to gravity. So if you're throwing something, or if I mention if you're dropping something, the acceleration, the pull on that is always going to be 9.8 meters per second squared, or negative 32 feet per second. So the acceleration is always constant. So if you look at any motion, any vertical motion on our planet, our acceleration is always going to be that particular number, which is how we found the acceleration due to gravity. Okay, so that's back to that. And then C, the last thing it asks us to do is when, if ever, did this thing change position on the s-axis? So when, if ever, did the particle change directions? Okay, so all right, you're gonna have to bear with me. I'm gonna sit this in 2 axes, even though it's technically not. So this is S and this is T. Technically, what we have is we have vertical motion. This is going to be our S-axis. But this T-axis is hidden when you're actually throwing. So if I throw something straight up in the air, technically you can graph it over time, but really you don't see the time axis here. So if I was to graph that 3t squared, if you're to graph this 3t squared minus 3t plus 1, I'm not sure what the parabola looks like, but let's just say it looks something like this. It's a parabola, it opens up, it looks something like that. So what we have is we have a motion of particles. So we know at time equals 0 was equal to 1 unit, right? And then it was moving in the negative direction. That's why it's going down. So the particle over time is going to do this. Now they're not evenly spaced. It might speed up in the beginning and kind of slow down at the end. So you might actually see something that looks like this. It goes here, here. I'm trying to make it perfectly horizontal. I blew it though. So this point would be here. This point would be here. This point would be here. The next point, this point would start going back up, and it'd start going back up, and it'd start going back up, and it'd start going back up. So really what you see is, you see this vertically, but if you want to graph it over time, it looks like this. But each one of these points kind of line up perfectly. So notice that this thing would change directions right here, that the particle changes directions right here. So that particle should change directions in that exact same spot, whatever that S value is. I'm not sure what this S value is. So notice that, what's the slope of the tangent line here? So what we know is that a particle will change directions when its velocity is 0 or when the derivative of s is equal to 0. So our solution to this one is it changes directions when s prime is equal to 0 or when v of t is equal to 0, because the derivative of s prime is equal to v. So, sorry, s prime is equal to v. So what we know is that that s was going to be our 3t squared minus 3t plus 1. So this is our s of t. So that means s prime of t is going to be equal to 6t minus 3, which is the same thing as saying v of t is equal to 6t minus 3. So when the derivative is equal to 0 is when this thing changes direction. So we're just going to find the horizontal tangent line. So then adding 3 divided by 6, t is equal to a half. So what we know is that this value here is at a half a second. All right, let's do something that's a little more real life. I'm going to give you an actual function. Let's do like I'm actually going to do like a paintball or something. It'd be kind of fun. All right, so come up with a cool example. So what I know is that vertical motion, so this is kind of known. I'm going to show you where this comes from. What I know is that vertical motion, if it's going to be in feet per second, vertical, on our planet, so this is going to be in feet per second, or in feet, is going to be our height, or our s, which is going to be our height function because it's vertical. Our s of t is going to be equal to minus 16t squared plus the initial velocity times t plus our initial height. So this is Earth if we're in feet per second. So our example is, assume I shoot a paintball vertically at 300 feet per second straight up. At an initial height of, we'll say about 5 foot, about my shoulder height. Determine the following. So I just want to answer kind of a bunch of questions here, and it's going to be kind of similar to what they're asking. So first thing I'm going to ask is, how long until the ball reaches its maximum height? No, this is when the ball changes direction, right? Just to make sure, that's when the ball changes direction. And then let's determine its max height. And B, I also kind of want to know how. Let's do this. Let's make B its max height because it's going to be a little mess. Determine its max height. C, I want to know its speed after 2 seconds. And then D, I want to know its acceleration. I want to know what the acceleration is, and then we can kind of talk about where that comes from. Okay, so solution. In pre-calc, what we do is we know that this is going to be a parabola, that S of t, or h of t, is going to be minus 16t squared plus my 300t plus 5, that your velocity goes here, your height goes here. So in pre-calc, we just find the vertex of this thing, so you'd have to complete the square. But in calculus, we can do a little bit better. We know that it changes direction is when its derivative is equal to 0, because really what this is going to have is, if you graph it over time, it's going to look like a parabola. I know it's just going straight up and straight down, but again, if you graph it over time, that time is going to make it look like that parabola. So what I need to do is I need to find the vertex of that parabola. But remember, the vertex happens when this ball is going to go up and it's going to turn around and go back down. So it happens when it changes direction. So for A, what we're just going to do is we're going to take we know this is when V of t is equal to 0, because again, this is when S prime of t is equal to 0. It's the same thing. V of t and S prime are the same thing. So the derivative of this thing is minus 32t plus 300. That's our V of t. And we're going to set it equal to 0. So minus 32t is going to be equal to minus 300. So t is going to be equal to 300 over 32, and they're both divisible by, I don't know, 2 at least. You know, I'm just going to give you a decimal. This is 9.375 seconds. Since we're doing word problems, we might as well use decimals. So it takes about 9.375 seconds. B, I want to find that max height. So what I know is that, remember, this is your position function, right? So if I want to know its position after 9.375 seconds, I take that time and I stick it into your position function. Position and height are the same thing. So B, what I need to do to find its max height is just plug in 9.375 into its position function. And this will tell me where it is. Oops. Should be, I have to screw that up. Minus 16 times 9.375 squared plus 300 times 9.375 plus 5, and I'm plugging out right in here. Minus 16 times 9.375 squared plus 300 times 9 plus 5. So I get about 1,411.25 feet. So this is 1,411.25 feet. Now I'm telling you, this is all real. Like if you do shoot a paintball gun at 300 feet per second, that's its max height. And this is how long it takes to get there. This is all how Earth works. So this was one reason why why calculus was created, so we can do this quickly. C, I want to know its speed after 2 seconds. Remember what speed is. Speed is the velocity, but its magnitude, right? So what I'm going to do is I'm going to take the magnitude of v of 2. Well, v is minus 32 times 2 plus 300. And I'm going to take its absolute value after that. I think it's positive anyway, so I think the absolute value is a little redundant here. But negative 32 times 2 plus 300, I get 236 feet. So, of course, after 2 seconds, this thing's slowing down because it's the fastest it's going is when you first shoot it. Gravity's pulling it in the opposite direction, so it's gonna slow down. You know what's kind of interesting is if you want to find the zero, you want to see how fast it's going when it hits the ground. You know, you can put this in the quadratic equation. You can find its zeros. And then you can just plug that t value into this velocity function, and it'll tell you how fast it's going when it hits the ground, which really tells you that's why you stay away from like projectiles that are coming back down, because they're going fast. So this is going to be equal to 236 feet per second. D asks for the acceleration. The acceleration is the derivative of velocity. Since velocity is this function right here, its derivative, a of t, which is equal to v prime of t, is going to be equal to negative 32 feet per second squared. The reason why it's second squared is because the derivative of the derivative means that you have that change of t on the bottom one more time, right? So I'm a little out of room here, but s, so what you're going to do is to find a of t, this is the derivative with respect to t of the derivative with respect to t of it's the second derivative of s, right? So we can see that's why there's 2 t's on the bottom, so that's why it's s squared. And that's our answers. Motion from a graph, I want to I'm going to do a picture. You know, I can just reproduce this picture. So I'm going to steal number 16 out of the book because I'm going to ask you guys to do number 15. So what we have here is something that looks like this, and what they're saying is that this is the position function, and they need you to from this position function, can we answer some other questions? So remember, this is the function 1, 2, 3, 4, 5, 6. Okay, so we're going from here to here. Okay. So from our position function, from our original function, I'm sure they're going to be asking what's the derivative and what's the velocity and so on. Okay, so this is s is equal to f of t. So what's your position function? So and this is, remember what this is. This is going to be equal to t, and this is going to be equal to s. So remember that that really what this represents is this is only vertical motion. That really our s-axis is just this, and we're just going up and down on this axis. So you don't really see t when you're going back and forth, even though you know it does live there. Okay. So when we're looking at that, they're going to ask for left and right. So they're really talking about this. Okay. So left and right. Okay. So left being positive and right being negative. Okay, so this is going in the positive direction, left, this is going in the negative, which is right, and this is going to be equal to 0, and this will be 2, and this will be negative 2, and then we still have negative 4. So it's the exact same. Okay, so when is P moving left? So when is it moving in the positive direction? Well, you can see that it starts here, right? So when it's moving in the positive direction is when it's going up. So it changed from 0 to 2, right? So it changed from 0 to 2. You got to make sure. I think I might have wrote that backwards. So I think left would be this way. I'm wrong. So it's actually that way. this is right, and this is left, because right is in the positive direction, and then left is in the negative direction. Okay, so you can see that it's moving right here. So if I was looking at that point, it's going to go from here to here in 1 second. Right? So this is 1, 2, 3, 4, 5, 6. So after 1 second, at second 0, it's here. At second 1, it moved to here. So it's moving right there. From second 1 to second 2, it's not even moving. From second 1 to second 2, it's staying beating. You can see that. So from second 0, it's right here. And then second 1, it goes right here. So it's going from 0 to 1, so 1001. So it moved 2 units in 1 second. Between second 1 and second 2, it's not moving. So 1001, 1002. So it stayed right there. Okay. Now from second 2 to second 3, remember this is time, second 2 to second 3, it moves to this -2. So I'm going to kind of go through the motion again. So I'm going to go 1001, 1002, 1003, just so it happens. So 1001, 1002, 1003. So at 3 seconds. So it was moving left to right from 2 seconds to 3 seconds, and moved from left to right. And then 1004, 1005, 1006, and this. Okay, let's start over again. So 1001, 1002, 1003, 1004, 1005, 1006. So that's its motion. That's how it looks. So we can say that it's moving from left to right. So A, so P is moving from left to right between 1 and 2. So 1 less than or equal to, no, sorry, I lied. Between 2 and 3, it's moving left to right here. So between 2x and 3. So between 2 and 3. Or you can say 2 to 3. It's also moving left right here in between 5 and 6. So, and 5 less than x less than 6. So this is going to be 5 to 6. So that's what it's moving left. Moving right, P is moving right. So in the positive direction. Well, it's moving in the positive direction from here to here. So we're here to here, and that's it. It's the only time it moves right. So just between 0 and 1 seconds. So 0 to 1 seconds. When is it standing still? Well, it's standing still here because it's not moving, and it's standing still here. It's not moving. So between 1 and 2, and 3 and 4. So P is not moving between so 1 to 2 and between 3 and 5. That's when it's standing still. Awesome. It asks us to graph. I want to graph its velocity. So I want to graph its velocity. Graph the velocity. So graphing the velocity curve, I'm going to put this back here. So 1, 2, 3, 4, 5, 6. Remember that v of t, that's wrong, that this is t and this would be v of t. That in order to graph this, remember that v of t is the derivative of s of t. So in order to find these things, we just have to find the slopes. So for instance, right here, the slope from here to here is rise over run. So this one, m is equal to 2 over 1, which is 2. For this one, m is equal to 0. For this one, m is going to be, it's a rise of -4, so m is going to be minus 4 over 1, so -4. Here, m is going to be equal to 0, and m is going to be, it drops 2, so for this one, m is going to be minus 2 over the difference between 5 and 6 is 1, so it's just -2. So the very first curve, I get 2, so it's got a slope of 2. So right there, it's going to go from here to here. Boom. This one is going to have a slope of 0, so here to here. This one's going to have a slope of -4, so 1, 2, 3, 4. So this is -4. It's going to go from here to here. -4 for that second. For this second, its slope is 0 again, so it goes slope of 0 for those 2 seconds. Then here its slope is down 2 over 1, so it's -2. So it's going to be from here to here. Now, the reason why these have all open circles is because at these sharp points, even though the function is continuous, its derivative is not, because the derivative here, the derivative for this one is 2 and the derivative for this one is 0. And since the derivative is a limit, the limit from the left, or its derivative from the left, is not equal to its derivative from the right. So at any sharp point, its derivative is not going to exist. So for a function's derivative to exist, it must be continuous and smooth. So any discontinuity, the derivative is not going to exist. Any sharp point, the derivative is not going to exist. That's why we have open circles. And that's it.